Hello, and welcome to this lesson in discrete structures of quantitative reasoning. We're going to talk about valid and invalid arguments. This is in the section we've already learned about logic and connectives and the conjunction and disjunction and conditionals and biconditionals. Maybe we've talked a little bit about implication. Implication is just the beginnings of what do we mean by argument. An argument is when you have a couple of things that you're told you assume are true, and then a conclusion is stated that will always be true if those two things are true. So it's the idea that this and this implies this other thing. So let's take a look at what an argument is. Let's take a look at this in more detail and how we can show them. So in mathematics and logic, an argument's not a dispute. It's not like we're having a fight. It's a reasoning process. So it's a sequence of statements that ends in a conclusion. Whether the argument is valid depends upon the form, whether that conclusion will always be true if the preceding statements are true. So you assume the preceding statements are true. We'll get in another video, we get into the idea of a sound versus a valid argument. For example, here's an argument. If Socrates is a man, then Socrates is mortal. Socrates is a man. Therefore, this word therefore means you are about to see the conclusion. And you can simplify that in mathematics. These three dots are often used to indicate therefore. Some texts just use a single dot on the last one. So the word therefore is the conclusion. The statements above the conclusion are called the premises. The premise. So I'm saying that if Socrates is a man, then Socrates is mortal. And that Socrates is a man. These two things I'm saying, and you just take that as truth. And then I'm saying, knowing those two things, you can conclude that Socrates is mortal. So whether this is valid or not isn't about Socrates. I could say if Rocky the Flying Squirrel is a man, then Rocky the Flying Squirrel is mortal. Rocky the Flying Squirrel is a man. Well, he's not, but it wouldn't matter. The form would still be correct. So that's the thing that gets students confused. So here is our form. Our two premises are here. I guess I can label them P1, P2. And this final thing here is the conclusion. So this is only about the form. You label your statements. P, B, Socrates is a man. Q is Socrates is mortal. You say if P, then Q, P, and then you conclude Q. Well, even looking at the form now, it kind of makes sense. Well, I told you if this happens, then this other thing would happen. Then I told you this happened. When it goes in the correct order, the conditional, when you confirm the antecedent. So some places call the statement before the then is the antecedent, and the statement after is the consequent. You may hear me use those terms. So in the abstract form, you set up variables. Any argument in this form happens to be valid. Now I can use a truth table to show that, and we'll talk about that in a bit, but this is valid by something called, the other thing that's called is modus ponens. Fancy Latin words we're learning here, but it's basically taking a conditional and saying, yes, the antecedent is true, and then you can conclude that the consequent happened. So it will make all statement substitute make the premises true and the conclusion is true. So an argument is valid when an argument is valid and its premises are true. The truth of the conclusion is said to be inferred or deduced from the truth of the premises. In other words, every time the premises are true, that conclusion will be true. A set of true premises that can lead to a false conclusion isn't valid. So really what you're concerned about, I'll go back to the prior slide actually, is, hey, if I make a truth table, I'm just going to want to see where are these two columns true, and then verify that this last column is also true. Where the premises are true will be called the critical rows of the truth table. So we'll move back to this slide. If you find that in a critical row of a truth table the conclusion was false, then the argument would be invalid or not valid. So here's how we proceed. We identify the premises and conclusion. We construct a truth table that shows the values of all the premises and conclusions. So each premise must have a column. And then a row of the truth table in which all the premises are true is called a critical row. Some books tell you to take all of the premises and AND them together. And then put your conclusion over here, and then you take all of these ANDed together. So wherever they're all ones is the only time you'll get a 1 here. So wherever they're all ones, you're in a critical row. And then you do an if-then to the conclusion. And the only time that if-then will be false is if you have ones in your premise and you have a 0 in your conclusion. So then you look at this column under the if-then and make sure it's all ones. That's one way some texts show you to show whether an argument is valid. The other way is to just look at the rows where all your premises are 1 and confirm that you don't have any zeros in the conclusion, because those are the only rows you care about. So we're going to learn this better by some examples, I believe. So you make a truth table, you indicate which columns represent the premises, which represent the conclusion, and sometimes you annotate the table. You tell me what your conclusion is when you're done. When you fill in the table, you only need to indicate the truth values for the conclusion and the rows. So you don't have to do all of the conclusion rows, only the ones where all the premises were true, because those are the critical rows. If you do the other form where you're doing if-then, you do all the rows and confirm they're all ones. But really the only ones that matter are the rows where all the premises are true. So we're going to determine the validity of this argument. So the first thing we need to do is establish our premises. Our premises are everything before the therefore. So we have 2 premises here. They're a little complex, but we can make a column for them in a truth table. And we have a conclusion here. So I do the truth table in the next slide. The conditional, in these, I wanted you to note that these conditionals are performed last in the order of operations. I would probably put parentheses around this if I were writing a test for you, just so you knew that the conditional was done last. But in the order of operations for logic, conditionals are done last if you're moving left to right with no parentheses. So we're going to find out that this argument is not valid looking at the truth table in the next slide. So there are your premises and your conclusion. So premises are here. I've labeled them. Conclusion is here. I'm looking for critical rows. I have a critical row here, here, because look, both of my premises are ones. The next 2 are not critical because there's a 0 in the premises. Here, this row is critical. So really, these 2 rows, this row, and I have a 1 and a 1. So I have 4 critical rows here. They happen to be rows 1, 2, 5, and 8. In those rows, now I drew the whole conclusion column. You could have just done it for the rows where you had ones in your premises. I'd like to fill the whole thing in, so especially so I can show you what I'm doing. So in this row, sure enough, I have a 1 there. I have a 1 there. So that row's okay. That row's okay. I don't need to check the next 2 because the premises weren't true there. This row here, I have an issue. If I look here, I've got a 0 in a row where premises were all true. So this issue means I have an argument that's not valid. You only need 1 row to mess it up for everybody else. So you can stop the video and take a look at how I made this truth table. You can go back a slide. You can go back in the video a little bit to confirm I did these premises correctly. I believe it's correct. But you make a truth table, and then the way you tell if the argument is valid, you have a column for each premise. Wherever all of those premises are a 1, or wherever they all AND to become a 1, you better make sure your conclusion is also a 1. If it's not, you have an invalid argument. So that is the process for using the truth table to determine the validity of an argument. Now, if you do these for enough simple arguments, you'll see there are patterns. There are certain arguments that always turn out to be valid. The one we started with the example with Socrates, was an example of that. If I say if P then Q, P, those are my premises, I can always conclude Q, and that will always be true. So we're going to talk about that in the next video. Thank you for joining.